In this video, we'll talk about harmonic motion as an application of trigonometric functions and their derivatives. So the idea of harmonic motion is the following. If I have a spring, and I hang a weight from the bottom of it, and I sort of displace the weight from where it would hang normally, so I pull it really far down and let it go, the weight's going to bounce up and down. So if I pull it down, the spring will stretch the weight, and then it'll bounce back up and the string will compress with the weight up here. So this process of the weight bouncing up and down is what's called harmonic motion. And the point here is if there's no air resistance, which doesn't happen normally, but if we assume there's no air resistance, then this weight will just oscillate down and up indefinitely, and so we can use trigonometric functions to model them. The fact that this works with trig functions has a lot of physics involved, but you can eventually show that trig functions are the way to go to model this sort of motion. Let's look at an example of a problem with this and see what we can say using our newfound trig derivatives. Assume that a weight is hanging from a spring, position s of t is 8 cosine of t, where t is in seconds, and s measures from the place where the weight would hang naturally. That's the other component of these problems. You have to set your 0 point to be where the weight would hang on its own if you didn't disturb it, and then you can sort of pull it down and let it bounce from there. But the 0 point has to be where the weight would hang on its own. I want to know what is the velocity acceleration as a function of time. Well, if my position is this s of t, which is 8 cosine of t, then my velocity should be how fast the position is changing, which is the derivative. So s prime of t, the derivative of cosine is negative sine. This becomes a negative 8 sine of t. And the acceleration measures how fast the velocity is changing. So it should be at that derivative, or the second derivative here, which is now negative 8 cosine of t. Let's think about these graphs and what they might look like. We'll do position in green, velocity in purple, and acceleration here. We draw some axes here. The position is 8 cosine of t. So that's going to start up at the top, because cosine of 0 is 1, and oscillate like this. The velocity is negative 8 sine of t. So it's going to do something like this. And then the acceleration is the negative of the position graph, so it's just going to go the other way. What can we see from this graph? Well, when is the object moving the fastest? Well, it's moving the fastest whenever I'm at these peaks here of the velocity curve, because that is when the velocity is maximized. Where is the object at that point? Well, the object is back at the center. So this also truly makes sense that if you're bouncing up down a spring, the object is moving the fastest as it passes through the middle, because then it has to start slowing down up near the top to then turn around and come back down. So the maximum speed is achieved at the middle point of the oscillation. And whereas the acceleration maximized, at least in magnitude, is at the opposite points. And that occurs when the object hits the peaks of its oscillation. So that's when the object feels the most force, is when it hits the peak and the acceleration has to turn it around, start moving back the other way. So those are just a few things you can tell from this picture, and things that you can now figure out because we know how to differentiate trigonometric functions, which can be used to model this sort of harmonic motion.